So if we get done with all of the stuff I went to today, this will be the last of the new stuff for the semester. And after this, it'll just be all tests and reviewing. So first of all, where we were at last time, we had figured out how to find B naught and B sub 1 as far as what is the y-intercept and the slope, where we use the calculators to be able to do it. We can do it by hand, and we did one by hand in class last time, and we did it by hand on our homework. And then today, or last time at the end of class, we were looking at how to use the calculators and put it into the tables and let the calculator do most of the work for us. But then the key thing, and that gives me the best fit line, but the main reason we want the best fit line is to use that for making predictions. And I was flying through this at the end of the class and didn't quite get to where I felt comfortable having you guys do anything. So kind of going through this a little slower to talk about what we're going here. If we're trying to use the best fit line to predict things, because that's really the purpose for it, is if I have data that's kind of trending, looking like this, well, maybe not quite such a nice S look going to it, more like that. If I have data that looks like it's following that kind of a pattern, well, if I can look at it and say, well, it looks like there's a nice line that kind of goes through the middle of it, and we can use the calculator and find exactly what that best fit line is. And that's what you're doing when you find your regression line. Well, if all my data tends to follow that pattern, then I can use that line, to help me predict what I think the values would be for something else. So, we've got these, but we got gaps between these. And so if I wanted to know what it was, somewhere in between here, what would be the best prediction for what I would have for the entire population now, not just from my one specific sample even, finding the point that's on that line gives me my best prediction if my line's a good line. The problem is if my line comes from data that looks something like that, well, there's not a good line that goes through that to help me predict anything. That looks like it's just kind of all over the place. If I find a line, and we might use the calculator, it might give us a line that has, gosh, I can't even guess what would be a good line on this one. All these lines really stink. Maybe I've got a line that looks something like that. Probably need to be a little less. But if that was my best fit line, I used my calculator, I found my best fit line, is that line a very good predictor of anything? No, because the points that I had aren't necessarily anywhere close to that, what that line looks like. And so trying to decide, is my line a good enough line to use as a good prediction like we had over here or not over here? So trying to figure out, well, what do we do then if I have something that's not a good predictor? And really, probably should have had as my best fit line on this one, looks probably more like a horizontal line would probably be about the best we could get on this one. It's probably a little bit better of a guess. But that's not going to be a good prediction. And so trying to figure out what to do when we have a line that stinks, how do I use it, or what do I do then to figure out the best guess of what that value is? What is my best prediction? So we use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. So even if I come up with this line as my equation, we can look at the data and look at the graph and say, that doesn't look like a great line for that. So if it looks like it fits well, then that's a good thing to be able to try to use my equation for. Use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables. So what you guys did on your homework from section 10.2 was to figure out that correlation coefficient R. And from there, you decided, compared to what was in the table, you decided if that regression line was a good equation or not, if it was a good predictor, if there was linear correlation or if there was not linear correlation. If there is linear correlation, so my R value is closer, is big enough, it's closer to either positive 1 or negative 1. So the absolute value of R, I guess I should say, is greater than whatever's in that table. If that's the case, we use the line as our best prediction. If my correlation coefficient's not good enough, so this correlation coefficient here would probably be closer to 0.1 which isn't going to be big enough to use. It's not greater than whatever would be in the table for however many points I have. If it's not good enough, we can't use my line as a predictor. Use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. So if I was looking at this data here, and I was trying to make a prediction, for stuff within this range here, I can definitely use my line as a good predictor. I can even go a little bit beyond. I can assume that we're going to continue these patterns for a little bit longer. I can't go way beyond. I could not figure out what it is when X is like way down here. That won't probably be a good predictor. Or I can't use what's been happening for patterns for the last 20 years and predict what it's going to be in the year 2100. I don't anticipate that what's happening in the last 20 years is going to be a great predictor for what happens 80 years from now. And so it's not going to be a good use of the things. We can only use it to predict close to. So maybe go out another 5 years. But trying to go out another 80 years is probably not going to fit our data well. And that's what you hear a lot of science that does a lot of that, where they say, well, based off what's happened in the last 10 years, when I was in college, recycling was a huge, new, major topic that everything was talking about. And so they were trying to predict how much garbage there was going to be in the year 2025 or something like that. And based off results of what was happening, if we don't recycle and all this stuff, we're going to have landfills everywhere you look was kind of the sound of things. And so trying to use that of what was happening as the patterns then and trying to predict 40 years later, 45 years later, not so useful. And things don't tend to follow those patterns for that length of time. And so trying to use those to go much beyond the scope usually doesn't fit data well. Use a regression equation for predictions only if the linear correlation coefficient R indicates that there is a did I go backwards somehow? I must have. If the regression equation does not appear to be useful for making predictions, the best predicted value of a variable is its point estimate, which in this case would be its sample mean. So when we're trying to make a prediction, if the equation stinks, the best estimate that we can do is our best point estimate, which in this case would be our sample mean. So let's look at a couple examples where we're talking about these. I guess before we do the examples, kind of looking at the strategy for predicting the values of y. I think this is in your book, is I think where this one's at. Is the regression equation a good model? So these are the things you have to know. The regression line graphed in the scatter plot shows that the line fits the points pretty well, so you need to look at the graph. You might use technology to look at the graphs. You don't necessarily have to plot the points for me to see that you've looked at the graph, but you need to look at the graph when you're doing these. R indicates that there is a linear correlation. The prediction is not much beyond the scope of the available sample data. If all of those are met, then that tells me my regression equation is a good model. You'll substitute the given value of x into our regression equation, which that regression equation was the y hat equaling b naught plus b sub 1x. I can use my equation if all of these are met. If any one of these is not met, then the regression equation is not a good model, which means regardless of the value of x, the best predicted value of y is the value of the sample mean, which is y bar. So on number 10 that we had done earlier, our equation that we had done last time by hand was that y hat is 3 plus 0.5x. Well, when we were looking at doing that, we did not have a value for x being 3. First of all, what was our correlation coefficient on this problem that we had done by hand on, what would have been, Monday? Monday, when we did this one by hand. You guys remember what we got for our correlation coefficient? I'm 90% sure that's the number that I keep remembering running into. Does that sound right to you guys? I don't think I have it written down here. Huh? Yeah. I know it was 0.8 something. Well, actually, I guess I should just look it up in the book because it's number 10. 0.816? Okay. So when we were looking at doing this problem, we had 11 points. From our 11 points, x being 3 was not one of our points. On number 11, our x values went from the lowest being 4 to the largest being 13. We got a correlation coefficient of 0.816, which we said was larger than what we needed. That with for 11 points, there's my little thing. For 11 points at the 0.01 significance level, we need to have 0.735, which is above that. So since that's the case, we have good correlation. We already graphed this one. Remember, our graph on this one was when we had a good straight line with one really bad outlier. So it fit the data well. So if that's the case, this one meets the qualifications, because 3 is not well beyond the scope. If I have the range of being 4 to 13, predicting what it was for 3 is not too far off. So since my equation is a good equation, the best guess of what y will be when x is 3 is to plug it in and see what we get. Well, if I substitute this in, half of 3 is 1.5. 1.5 plus 3 gives me 4.5. So my best prediction of when x is 3, what do I expect to get out for y, is 4.5. Questions? If we look at number 6 on page 547 then. On number 6, we're looking at the heights of mothers and daughters. A sample of 8 mother-daughter pairs of subjects was obtained, and their heights in inches were measured. The linear correlation coefficient is 0.693, and the regression equation is y hat equals 69 minus 0.0849x, where x represents the height of the mother. The mean height of the mothers is 63.1 inches, and the mean height of the daughters is 63.3 inches. Find the best predicted height of a daughter, given that the mother has a height of 60 inches. So a lot of information going on there. First question I have is the equation a good model? So, thumbs up if you think it's a good model, thumbs down if you think it's a bad model. I have a lot of thumbs not moving. Where do I even start with trying to decide if it's a good model? Okay, I'm going to look at my little table. As I look at my little table, where do I start? Okay, the number of ordered pairs was 8. So if we're starting with 8, that means to be even at the 5% level is 0.707. Do we meet that? No, we're at 0.693. And it's always the absolute value of r that you're comparing to this. So if you had a negative correlation coefficient, you take it and make it positive to compare it to it. So it's not good enough. If it's not good enough, and again, it only has to meet one of these criteria, and the fact that it does not meet the fact that r is good enough, that's kicking me over here. Regardless of the value of x, the best predicted value of y is the value of y bar. So in this question, what's that mean? Okay. So the y bar would be the mean height of the daughters, because that's what we're trying to find. So what is the mean height of the daughters? Okay, 63.3 inches. So the best guess that I can have for what the height of the daughter is going to be is 63.3 inches. This is telling me that there's not a good correlation between the mother's height and the daughter's height, that I cannot use the mother's height to predict the daughter's height. Now, it's giving me a correlation. It's got a relationship at that 0.693 level, so it's got some correlation. But there's enough other outside factors that I can't use that as a good predictor. It's just not good enough to use to predict it. Just because my mother is tall doesn't mean I will be tall, or just because my mother is short does not guarantee that I will be short, because obviously the father's height has some impact on that. And so there can be, and even genetics, that somebody that comes from two short parents can still be a tall person sometimes, if it goes back to the grandparents' generation type things. So you've got those recessive genes that are in there that can have some impact also. Questions? Oh, I want to do another example. I thought I had another good one in there. Let's do number 14. Number 14 is find the best predicted cost of subway fare when the consumer price index is 182.5 in the year 2000. So where do I start? Okay, so first we need to figure out what our correlation coefficient is, which is also going to help us find our equation. So put those in as list 1 and list 2. After I've put them into my two lists, where do I go next? Okay, calculate number 4, which is your linear regression. As long as you put it in as list 1 and list 2, you can just hit enter. So there's my data. I'll figure out what to do with it. Six data points, okay. So for my 6 data points, what is my critical value that I have to use? Okay, so for your 6 data points, we're looking at the 0.811. So are we there? Okay, we've met that criteria. Yeah. So my R value would be the 0.978, which is definitely better than the 0.811. If I graph it, so we're going to go to Zoom and do number, whatever it is it 9? Yeah, number 9, which is Zoom Stat. It looks like there's a pretty good graph going. If we look at what our equation was, what is my equation this time? Aaron, you look like you have problems first. All right, we'll go back and go to your second and calculate, or second and catalog. Catalog. 0. Go clear down to diagnostics on again. And then it should be back. So for my example, since R is the 0.978, first of all, what is my equation? What is B naught? Negative 0.124. Are you getting different numbers than me? Is anybody else getting the same numbers as me? Maybe I should make sure I'm got the right answers. Okay. Okay. So B naught is the negative 0.124. What is B sub 1? So that's your A, which is the 0.00955. And so that is my best equation. So this is number 14. So my equation is that y hat is the negative 0.12425 plus the 0.00955x. If I put that in as my y equals, just to see if it does look like it's good enough. So if I go back to my y equals and put this equation in there, and go ahead and graph it, because I've already done the Zoom stat, so I've got those points graphed. Does it look like it matches pretty well? Okay, so it looks like my correlation coefficient says it's good enough. It looks like it's a nice straight line pattern. Therefore, if I am wanting to predict, that tells me I can use this equation to predict then. So my best prediction for the subway fare when CPI is 182.5, where do I put the 182.5? Okay, I'm going to put that in for X. Now, for those of you guys that have already done this in college algebra also, if you go to second and table, oops, actually I guess I'm going to do this first. Do second and table set. On table set, if you make your independent variable the ask variable and your dependent the auto, that means you can put in what you want and it'll calculate it for you. And then you can do second and table, which is right above graph. And I can now put in my number of 182.5, and it gives me my y value is the 1.61. 1.6186, I guess I should say. And since what I'm predicting is subway fare, this makes sense to round it to the dollars and cents, so $1.62 is my best prediction. So if the consumer price index is at 182.5, I anticipate that subway fare is going to cost me $1.62. Questions there? And that is just putting that in for the X. If you don't use the table, you can still just put it in for the X, where I take out the X out of my equation and I replace it with the 182.5 and just do the arithmetic. Now, that's my best prediction this time, is that y hat is $1.62. Because my correlation coefficient, R, was large enough that says that's the best equation. That the price of subway fare does change based upon the CPI, Consumer Price Index. What if it didn't? what if this was just not good enough? What we did say that if it's not good enough, so pretending, I'm going to change my R value because I don't want to change equations. What if my R value came out to being 0.614? If that was the case, could I use this equation? Okay, if that was the case, I could not use this equation. How can I use my calculator and find my best prediction? Okay, I need to find the mean of which one, the x's or the y's? Okay, I want to find the mean of the y's. How can my calculator find the mean of the y's instead of me having to redo it all? Okay, go to Stat, Calculate. Okay, doing that very first one, the one variable statistics. Now, I want the one variable statistics of the y's, which I put in the second list. And so you have to do second and list 2. So second and number 2 to get that I was doing for the list. Otherwise, if you just do one variable statistics, it's going to find the mean of the x's, not the mean of the y's. So what would be my best predictor? Okay, so $1.06. So that is the mean of the y's. In this case, that's not the best thing to do, though, because my R value was better. You're still having issues, aren't you?
I've tried it. The numbers are correct.
They're not. $162.2. Oh wait, did I go into the wrong spot? I did. Yeah, I got sidetracked. Never mind. Yeah, those are right. I should look at number 13, so 14. Oh, there's the problem. The frequency list is list 1. Oops, make that frequency just number 1. Oh. Nice try. right, well, I made it work. I want to play with it again afterwards. It shouldn't do that. Okay. Other questions? Because what I had to do was, because it wanted a frequency list, each number was only getting used once, or each point was only getting used once. So I had to make a new list that just was a list of ones, so that I could put that as being your frequency list. Yeah, it is. And that's why I'm trying to figure out what the trick is that I'm not noticing. It's helpful if you've got the same ordered pair that happens a lot, though, to make a list that says, okay, I don't want to type the number 5-2 in there 6 times. The new list just says, okay, it happened 6 times. So that's why it's got that there. It's just kind of a pain at this point. Okay, questions on using those. I will tell you the biggest mistake that you guys will make on section 10.3 is that you will forget to pay attention to, is my correlation coefficient good enough? And you guys go to the effort of getting the equation, because these will ask you first find the equation. When you find the equation, you're automatically getting your correlation coefficient with it, because that's part of the whole calculation. You will forget to check, is my correlation coefficient good enough? And you just get used to, let's plug the number into the equation I just found, and thinking it has to work. It will not always work. A lot of times it does. A lot of these problems, we have intentionally found that there's a correlation between two things. And so if there is a correlation between two things, then we use that equation. But if there's not a correlation, don't force yourself to use the equation when the equation's not good enough to use. Questions there? All right, let's go ahead and start it on the contingency tables. I can tell you we're not going to get done with them today. So our test will be on Wednesday. But go ahead and get started on our contingency tables. A contingency table, or a two-way frequency table, is a table in which frequencies correspond to 2 variables. One variable is used to categorize the rows. A second variable is used to categorize the columns. Contingency tables have at least 2 rows, and they have at least 2 columns. I've been helping the Trenton schools were asked to help with the Grundy Health Department had conducted a survey where they were asking people their opinion on smoking and whether they should allow smoking in, I don't remember the questions because it's been about a month ago that I looked at the questions. We've just been looking at the data lately. But they were asking questions like, should smoking be allowed to be done in public parks? Should smoking be banned from restaurants, I think was one of their questions, and just getting public opinion on what was going on with this. Well, once you get all the data from all the public opinion, now trying to figure out what to do with that. And is there a relationship between whether the person's a smoker or not and how they answered these questions? Whether the person, they were also looking at what part of Trenton it was from, because you guys are having different, is it zones? Is that what they call them? I don't know. There's different areas of Trenton. And it's not the townships. I don't remember what it's called for you guys. You've got different areas of Trenton. And so based on what area you were living in, did that influence how you answered these surveys and that type of thing? And so it's looking at these contingency tables. I thought I had a good one example. There's a contingency table. This is one we're going to be using a little bit here soon, where this is an example of a contingency table, where this is looking at a baseball stadium and whether or not the dome is opened or closed compared to if the team wins or loses. And so you've got 2 different sets of data that's going on, and you're looking at how many people from each group had that. So how many people that live in Zone 1 of Trenton answered that they think we should put a rule where you can't smoke in the public parks, compared to people that live in Zone 1 that say you shouldn't put a new rule in, compared to Zone 2 and same kind of thing. And so looking at those and seeing if there's a relationship between those kinds of things. This is not where it can be written as ordered pairs, because these are not quantitative data, because what township you're in is not a number. Even if we call them townships 1, 2, and 3, there's no township 1.5, or not township, but zones. Zone 1.5 doesn't make sense. You're either in zone 1 or you're in zone 2. And so the numbers aren't significant as far as what they're saying. It's just a label. Same as calling it zone A, zone B, zone C. And so since those are just labels, you have to use these as contingency tables to see if there's a relationship. So if we, I guess I had an example right here. Number 8 on page 607, which is the one I flipped to really fast. In a recent baseball World Series, the Houston Astros wanted to close the roof on their dome stadium so that fans could make a noise and give the team a better advantage at home. However, the Astros were ordered to keep the roof open unless weather conditions justified closing it. But does the closed roof really help the Astros? The table below shows the results from home games during the season leading up to the World Series. Use a .05 significance level to test for independence between wins and whether the roof is open or closed. Does it appear that a closed roof really gives the Astros an advantage? And so looking at the number of wins compared to the number of losses when the roof was open compared to when the roof was closed. So in this case, my rows, the ones going across, are the closed roof and the open roof. The columns, the vertical, is the number of wins and the number of losses. And my question is just looking, is there a connection between those two things? Is there a relationship between win-loss record and open-closed? So we're doing a test of independence. A test of independence tests the null hypothesis that in a contingency table, the row and column variables are independent. That means there is no connection between the two. Sounds very similar to what we just did with our regression equations and finding our correlation. That we were always testing the null hypothesis that there was not a correlation. My alternative hypothesis was that there was a correlation. Now my alternative hypothesis will be that there is a connection between those two, that they are dependent. So I'm always testing independence. And this is a huge one to remember because that is telling you what you're doing and what your answers give you when you get to the end. So when you're doing these contingency tables, your null hypothesis is always that they are independent. But there is not a relationship between the two things. Questions on that? Now, on this one, the notation is different than the notation we've used on anything else. O represents the observed frequency in a cell of a contingency table. That's the number you're getting in here. In this case, they had 36 wins when the roof was closed. That would be O for that cell. That is what was observed. You would have, for the survey that was taken by the Grundy Health Department, you can have that there were so many smokers that thought that we should put a law in place in Trenton that they can't smoke in the public parks. That would be the observed frequency. E represents the expected frequency in a cell. That is found by assuming that the row and column variables are independent. And we'll figure out what that formula looks like, where we're assuming that those things are independent, that there's not a relationship between those two things, and what would be the expected value that would just happen anyhow. R represents the number of rows in a contingency table. Don't include the labels. So this one had 2 rows. We had the closed roof, we had the open roof. C represents the number of columns in a contingency table. Again, not including those labels. The requirements that have to be met. First of all, the sample data are randomly selected. Now, this is where the Grundy County Health Department survey already has failed, is because they didn't make sure that it was a nice, simple, random sample. It was more of a convenience sample. Those people, because I think they sent it to everybody in their bill, and whoever answered their survey were the ones that are now in this data results. So it failed on the first requirement. The statistics students are still going to continue using this because they needed to be able to report it back to Grundy Health Department, and they're going to include as part of their presentation the fact that the sample statistics are not a good sample or random sample, therefore it kind of nulls most of their results anyhow. The sample data are represented as frequency counts in a two-way table. So you have to have the rows and the columns and looking at there. For every cell in the contingency table, the expected frequency E is at least 5. So you have to expect at least 5 values in each piece. There's not a requirement that every observed frequency has to be at least 5. And there is no requirement that the population must have a normal distribution or any other specific distribution. So what you observe doesn't necessarily have to reflect what's expected out of it. But you had to expect at least 5 in each of those cells. So again, our null hypothesis is always that the row and column variables are independent of one another. Your alternative hypothesis is always that the row and column variables are dependent. Those will not change. Just like when we were doing the correlation, that the null hypothesis was always that there was not a correlation between them, with the alternative was that there is one, that it had to meet the requirements to be extreme enough that we can say there's a relationship between them. Here, the requirements have to be extreme enough to say that they are dependent. So it's always a test of independence. It's what you assume to be true with that null hypothesis. And we will look at how to calculate the test statistic next time. So that's where we'll stop. Oh, you need your homework, though. Nice try. Okay, so do not do anything from page 606 yet. But do the page 547. You already did 13 by hand, so you don't have to do 13, so just 15 to 27 odd. And our test is going to be on the 29th. So on Monday, I will finish this chapter, and I will give you guys the review for the final, and we'll start looking at a few things from that first on Monday. Do what? Extended problem. Oh yeah, I didn't put an answer on there. Let's go ahead and still make that Wednesday. That way I can get you guys back the extended problem before you have to take the final, so you can have a better idea of where you stand. And our final, pretty sure that's the right date, isn't it? May 8th from noon to 12, or noon to 2. Yeah, noon to 2, last possible date for you guys. And you've got graduation practice from 10 till whenever. You don't.